1.5 miles from touchdown. Turn left heading 052. Heading 052. Dropping slightly below the glide path, ease it up a little. Turn right heading 054.
There are many problems to resolve in establishing a choice of landing aids. If all aerodromes were situated in such a way that the approaches to the runways were over level ground, if the availability of funds was no problem, if states were agreed on the kind of approach system that should be used, if only one type of aircraft had to be considered, then it would be easier to draw up and implement international standards on precision approach and landing aids. But all aerodromes are not so situated that the runway approaches are free of mountains, hills, and water. Budget problems do exist and vary from aerodrome to aerodrome. The amount of money available for approach and landing aids is related to the amount of traffic handled by the aerodrome, and these aids, which include runway approach, threshold, centerline and edge lighting, the visual approach slope indicator system, the instrument landing system, surveillance and precision approach radar, are very costly, not only to buy and install, but also to man and maintain to the high degree of reliability required. States have different ideas on the kind of approach system that should be used. The aircraft to be considered vary widely, from large, with approach speeds of 160 knots and more, to small, with approach speeds of less than 60 knots. Then, too, meteorological conditions are not the same at all aerodromes, and the approach aids needed to provide aircraft with adequate guidance to touch down at night in a blinding snowstorm are very different from those needed where the air is clear and dry for most of the year. With considerations like these making for variations in approach systems, it is remarkable how closely approach and landing aids throughout the world follow the international standards and recommended practices ICAO has established. Before we go any further, let us look at some drawings showing the different approach aids and how they are integrated. First, we have a simple profile with the runway on the left. This line across the runway is the threshold. It is not necessarily the end of the runway. Sometimes it is displaced inward. This is the projected runway centerline. Following a normal approach, we would first come to the outer marker, which indicates that we're about 3.9 nautical miles from the threshold. The outer marker beacon is identified by continuous dashes of a 400 cycle tone at the rate of 2 per second. Continuing on, we intercept the middle marker about 3,500 feet from the threshold. The middle marker transmits alternate dots and dashes of a 1,300 cycle tone. Here we have a scene of the middle marker installation. Finally, we reach the inner marker, which when installed is between 1,000 and 1,500 feet from the threshold. This marker transmits at the rate of 6 per second, continuous dots of a 3,000 cycles per second tone. All markers transmit at 75 megacycles. The outer marker serves as the first positive fix to an aircraft on an ILS approach. The middle marker is located so as to indicate the imminence, in low visibility conditions, of visual approach guidance. That is to say, in low visibility conditions, the pilot may expect to see the runway approach lights after this point is reached. The inner marker, when installed, is located so as to indicate, in low visibility conditions, the imminence of arrival at the runway threshold. If we were to draw a line perpendicular to the surface of the runway at the point where the center line and threshold line intersect, and were to extend this vertical line to a height of approximately 50 feet, we would have located the ILS reference datum. This is a point through which the ILS glide path passes, regardless of the chosen glide path angle. When the glide path angle is 2.5 degrees, the projection of the straight line portion of the glide path on the runway center line would be just over 1,100 feet from the threshold. The angle of the glide path is governed by a number of operational criteria, such as acceptable rates of descent for the types of operations envisaged at a particular aerodrome, the position of obstacles in the approach area, local meteorological conditions, runway length available, and operating limits envisaged. Where the application of such criteria permits, the preferred angle of the ILS glide path should be 2.5 degrees. The radiation from the UHF glide path antenna system produces a composite field pattern, which is amplitude modulated by a 90 cycles per second tone predominating above the path and a 150 cycles per second tone predominating below the path. This is the glide path antenna. The checkered building houses the electronic equipment associated with the antenna. There are many monitoring devices to assure an accurate radiation pattern. A number of conditions, which include maintenance of glide path angle and power output, must be satisfied, otherwise the glide path would be turned off. The masts here are for the purpose of detecting any changes in the glide path which might occur. While we have this profile in front of us, we might briefly mention the VASIS, or Visual Approach Slope Indicator System. These lights, which provide an approach angle reference for the pilot, are engineered and installed to be compatible with the UHF glide path beam. We will see this system during an actual approach later in the film. Now, looking at the plan view, we again have our runway with its visual markings. The L would indicate the left of two parallel runways. The 20 indicates the runway heading, using only the few digits of its magnetic heading rounded off to the nearest 10 degrees. When the threshold is displaced inwards, it would be marked as we see here, with the transverse strip indicating the displaced threshold and one or more arrows pointing to the threshold. 500 feet beyond the threshold markings, we come to the first pair of touchdown zone markings. Farther along, at 1,000 feet, we have the fixed distance markings, which are put here as a readily definable reference point for the pilot to help him determine his point of touchdown. Runways longer than 7,000 feet would have 6 pairs of touchdown zone markings. And again, in the plan view, we have the visual approach slope indicator lights, 12 in number, placed with reference to these points. There are 6 on each side of the runway in 2 rows. The localizer of the ILS is beamed by an antenna from the end of the runway opposite to the direction of approach. Similar to the glide slope, the localizer beam is monitored by various sensing devices such as we have here. In addition, manual checks, and from time to time, flight checks are made with highly instrumented aircraft. This navigational beacon projects along the center line of the runway and out along the extended center line to a distance of 25 nautical miles. This is known as the front course of the localizer. The localizer is considered to be a very straight, narrow beam, but the difficulties of keeping the beam within operationally acceptable limits are very considerable. Like the glide path, the localizer is a composite field pattern made up of amplitude-modulated 90 and 150 cycles per second tones, with a carrier frequency in the 108 to 112 megacycle band. The 2 fields are projected in such a way that the 150 cycle tone will predominate on the right of the course as one faces the localizer antenna, and the 90 cycle tone will predominate on the left. The signal is interpreted by the localizer receiver in the aircraft and displayed on the course deviation indicator. For the purpose of explanation, we will depict the localizer beam like this. The glide path like this. And focus our attention on this course deviation indicator. If we allow our aircraft to drift to the left of the localizer, we see the needle deflect in the opposite direction. We must think of the needle as the runway and fly towards it to get back on course. Drifting to the right, we have this situation. Now our rate of descent is too slow, and we are above the glide path with the needle deflected downwards in the opposite direction. We fly down towards the needle to bring us back on the glide path. The needle is deflecting towards the glide path, and once again we fly towards the needle. The same guidance information is displayed in the more sophisticated instruments, such as this attitude director indicator. A similar response is required. That is, fly towards the needle. There are 6 conditions in which an aircraft can be landed. The first is known as VMC, or Visual Meteorological Conditions. In this condition, the pilot has full visibility, although he may still have turbulence, wind, and other factors to contend with. The remaining conditions exist when visibility is impaired by adverse weather. The pilot is then faced with what is called IMC, or Instrument Meteorological Conditions. In IMC, the pilot must turn to approach and landing aids for assistance. These conditions are identified as Category 1, Category 2, Category 3A, Category 3B, and Category 3C. There are 2 critical values for each of these 5 categories. There is the decision height, which is the height at which the pilot decides whether it is safe to land or whether he must execute a missed approach. And there is runway visual range, which is the range of visibility along the runway at the point of touchdown. The values for Category 1 are these. For Category 2, for Category 3A. Category 3B, and for Category 3C, we have conditions requiring a completely automated flare-out and landing. Complementary to the electronic approach aids are the visual approach aids. The lighting systems for both Category 1 and Category 2 approaches extend out 3,000 feet from the threshold. For Category 1, they can be either of these 2 presentations. For convenience, we will refer to the overall pattern in terms of inner, middle, and outer 1,000-foot sections. You will notice that in addition to the crossbars, the right-hand pattern has a center line composed of 3 lights in the outer 1,000, 2 lights in the middle 1,000, and 1 light in the inner 1,000-foot section. The left-hand pattern has its center line composed of barrettes and a crossbar for roll guidance 1,000 feet from the threshold. This system is supplemented by condenser discharge lights. Here, in an actual approach, we see the condenser discharge lights, which are flashed twice a second. The discharge begins with the outermost unit and progresses towards the threshold. There is provision for switching off the inner 1,000 feet of the condenser discharge lights immediately and separately from those in the middle and outer portion of the system when they're too intense for the pilot. This is the lighting system for Category 2 approaches. The middle marker, you will recall, is 3,500 feet from the threshold. You can see then that as a pilot receives an indication that he is passing over the middle marker, which is 500 feet before the approach lights begin, he would be approximately in this position. In Category 2 precision approach lighting, the inner 1,000 feet before the threshold has red side row barrettes every 100 feet. A barrette is 3 or more closely spaced lights that appear as a bar of lights. Preferably, these red barrettes should be 30 feet on each side of the center line. The pilot can ask for a reduction of intensity in the entire approach lighting system. Most installations have a 5-step intensity control so located that the tower controller can conveniently make this adjustment when requested. The threshold is lighted by a row of green lights spaced 10 feet apart across the full width of the runway. When additional conspicuity is considered desirable, an extension of the threshold lights is provided. These extensions are called wing bars, and they extend at least 35 feet outward from the edge of the runway. Runway centerline lights are white lights spaced longitudinally at 25 or 50-foot intervals, though when high-intensity lights are used, the spacing may be 100 feet. 30 feet on either side of the runway centerline are the touchdown zone lights, which are white barrettes placed in such a way as to seem to be an extension of the red barrettes. The touchdown zone lights are spaced at 100-foot intervals along the first 3,000 feet of the runway. Finally, there are the white runway edge lights. There is a preference for placing these 75 feet on each side of the center line with a longitudinal spacing of 200 feet for an instrument runway. We have been examining the aids that are interpreted by the pilot. There is another aid that is monitored from the ground, and it is the precision approach radar. Radar, with its ability to see an aircraft in fog, cloud, rain, or darkness, provides an ideal complement to the instrument landing system. With this aid, the pilot can be given both assistance and reassurance by the controller on the ground. While the precision approach radar can be installed as shown in this example, there are many factors which affect the choice of site for such an installation. The PAR shall be sighted and adjusted so that it gives complete coverage of a sector with its apex at a point 500 feet from the touchdown point and extending plus or minus 5 degrees about the runway centerline in azimuth and from minus 1 degree to plus 6 degrees in elevation. The objective is to align the horizontal and vertical sweep of the radar in such a way that they will be compatible with the ILS glide slope and localizer. In the approach control room, the precision approach controller directs the aircraft to a point where the pilot has to decide whether he has enough visual guidance to land his aircraft or not. The combination of the pilot following the ILS with the instrument in the aircraft and the precision approach radar controller monitoring the aircraft's distance, azimuth, and elevation gives a very considerable margin of safety in approaches during minimal conditions. The blip of an aircraft can be seen as it descends on glide path.
Heading 062. On course, still slightly to the right. Turn left heading 060. On course, on glide path. Heading 060. 3 miles from touchdown. You have been cleared to land. Gears should be down and locked.
On this azimuth display, we have the blip continuing on towards touchdown.
Heading 060. Turn left heading 058. On course, very slightly to your left. On glide path, on course.
In our examination of both the approach profile and plan view, we have shown details of the sighting of the visual approach slope indicator system. Now we have an opportunity to see the actual installation of these lights and how this aid is interpreted by the pilot. While this aid is useful in daylight approaches, we have waited until dark to make this approach. We can see ahead the white and red bars of the Vossie's lights, indicating that we are on the correct approach slope. Since we are descending too rapidly and are falling below the glide path, the downwind bars have also become red, indicating we're too low. The pilot reduces the rate of descent, and we regain the correct approach slope. During this flight, visibility has been ideal to permit us to see the Vossie's display, but the going is not always so good. When conditions are like this, the pilot needs all the help he can get. Above all, he needs confidence in the accuracy of the aids on which he is obliged to rely. The engineers who design, or those who go about the unheralded routine of maintaining accuracy in their equipment, are deserving of recognition and appreciation by all whose safety is dependent upon these systems.